had sincerely intended to be here. So we've also rearranged the schedule. The next speaker will be Professor Berkeley, the 1996 winner of the Nobel Prize in Physics, and Professor Emeritus at Stanford University. I could go down and go through the list of where he's been and his achievements in Cornell, Bell Labs, and the later part of his career at Stanford. But the most important characteristic or trait that he has is of being a very entertaining speaker, which I'm sure I was heard him speak here last year, and I'm sure that the speech today will be just as entertaining. Without saying more, I'd like to introduce the lecturer.
今天天气好极了。For those that speak Chinese, or at least have a wife that speaks Chinese in my case. Anyway, it's my pleasure to be here today. Now, I must say that I thought Charles gave a spectacularly good talk. And I was already worried because my talk actually had rather little to do with any of the other talks, because I guess I had my head somewhere else. Anyway, and so then Charles gives this wonderful talk, and I just hope that I will not put you to sleep. This is actually a collage of two different talks I give. And at least I think it starts out with a very nice picture of the Earth, but in fact, well, this is I think this is the Red Sea, I believe. Anyway, so let's go on. I have lots of favorite slides because I'm an avid photographer. So this is another. So you get actually two different first slides: how science changes our lives and how advances in science are made. And I'll talk about both of these things because they're obviously interrelated. This, of course, is the Golden Gate Bridge, and so we all know about that. Anyway, so we're starting out with Nicholas Copernicus, which I think we all know who he was and what he did. But you know, he was really the first really serious scientist, I would say. Unfortunately, I can't. If I get back up here, I think I can probably read this a little bit better. Anyway, Copernicus was in fact a spectacular person. But I think the next person in line in terms of really great scientists was Galileo, and it's really hard to top Galileo. Galileo was considered the father of modern astronomy. He did a lot to improve the quality of telescopes, and he, of course, was the first person to actually see the four largest moons of Jupiter. But we're going on, and it gets better and better, I suppose. Now, this, of course, is Sir Isaac Newton, and the fact that the French would actually put an Englishman's picture on one of their postage stamps suggests how great the French consider Sir Isaac Newton. And it's kind of interesting what it says here. We perhaps owe more to Sir Isaac Newton than to any other early scientist. He developed the mathematics of calculus to understand particle motion, and the idea of a gravitational field helped to explain the motion of the planets. And then this is what Sir Isaac Newton said about himself. I do not know what I may appear to the world, but to myself I seem to have been only like a boy, playing on the seashore and diverting myself into now and then finding a smoother pebble or a prettier shell than ordinary, whilst the great ocean of truth lay all undiscovered before me. So you can imagine how, I mean, you can get some feeling for what was going on in Newton's mind. This, I dare say that James Watt was not a scientist. He was really an inventor. It's kind of interesting. I didn't show you, but typically what happened is that I chose scientists such that one of them died just before the next one was born. And anyway, so this is James Watt, and what he did really was to greatly improve, using thermodynamics, greatly improve the efficiency of steam engines by roughly a factor of 4. That really made a lot of difference. But in fact, what it did was it allowed the industrial age to come. So unfortunately, once you start burning coal, you end up with a terrible effluent. And I dare say that thanks to what Watt did, I suppose, for quite a long time, we had major cities had air that was fouled by the not just the carbon dioxide, but a lot of worse things that comes with the burning of coal. So this is the Lake Powell. It's during a period of drought. And now you can see we have, if I go back here, these are 2 smokestacks. Here we actually, oops, there we go. So here we have 3 that probably are burning more coal than what I just showed you. But these are modern coal-fired electric generating plants, and they scrub the effluent that's coming out. They get rid of the particulate matter in particular. You can't get rid of the CO2 that way, but it ends up looking fairly clean. However, if you look on a longer scale, here now are those 3 electric generating facilities. And if you look coming out here, in fact, there is a wisp of sort of a brown haze, which is a result of the burning of the coal. Otherwise, everything else is the same here. So, I mean, one can do a lot with falling water, and so certainly if you want to choose a clean source of energy, probably the cleanest is a hydroelectric plant. So this shows how it works. I think everyone can imagine. This is basically the water comes down, it turns a turbine, the turbine turns a generator, and this is a blow up. This is the turbine, and this is the generator. These generators, by the way, are typically something like, I would guess, maybe 30 feet in diameter. I've seen these things up close, and they're really remarkable. This is Itaipu, which I think there's a big argument as to whether that is the largest electric generating plant in the world. This is at the border between Paraguay and Brazil, and so the generator is above this floor, and the turbine is below this floor, and this shaft is about 4 feet in diameter. To give you some idea how big and how strong these things are. And this thing makes absolutely no noise. It's really remarkable. But now let's get back and see what, I mean, for a long time we didn't use falling water. In fact, of course, there's a limited amount of energy one can get from falling water. But this shows over 1,000 years what CO2 has done to our atmosphere. So here we're actually looking at the average temperature. This is from year 1000 to 2000. And what you see is that very kind of slowly the average temperature measured by a number of different means is slowly dropping. But then, just in the last 100 years, in fact, there's a very sharp rise. And this is really due to our mostly burning of coal, fossil fuels. This is a CO2 in the atmosphere. This is basically determined by looking at bubbles of gas trapped in ice. And so it's pretty steady, but then again, about 100 years ago, this started a very sharp upturn, and this is CO2 in our atmosphere. If you look at this, compare this with our estimate of the carbon emissions that have occurred over the last few hundred years, you can see there that basically all of these upturns are essentially the same thing. And this is really a problem that we have, that I dare say there are ways of generating electricity that don't involve burning coal, but coal is in fact the cheapest way of doing that. It's not the best. So this is shows the melt of the Arctic ice sheet over different periods of time. These are different years. So 1979 here, it started turning up rather quickly. That this is as you're cooling back down. But if you compare this is 1979, and this is what's happening in 2007. You're losing a lot more ice 2007 than you did in 1979, and you know there's just no way of compensating for this. We are in fact warming. We are both the fact that we are putting a lot of CO2 into our atmosphere. CO2 actually has the effect that it reflects infrared back to the Earth. And so it's not just that the CO2 can't get out. In fact, it's actually reflected back. So NASA, by the way, has in fact satellites, which I like to say that they're down-looking satellites. They actually measure the CO2 concentration in our atmosphere. But in fact, measuring something and doing something about it are entirely different things. So you might ask, how is the U.S. doing? Now, I choose the United States. There are lots. I dare say it's easy to choose the United States because we are the worst country in the world, I think, in terms of per capita production of CO2. Per capita, the U.S. consumes the energy equivalent of 3 million megawatts of energy constantly. Most of this is from CO2, but not all of it. 1,000 watts per person. I very quickly realized before I ever read that number that in fact I was using about 1,000 watts as a homeowner. So this is over 4 times the world average and twice the consumption of the European countries. The United States is really a bad actor when it comes to particularly, I would say, the CO2 problem, but in general, we consume more than our share of energy. Our strong dependence on oil makes the U.S. vulnerable to strong fluctuations in petroleum prices as the world begins to run out of petroleum. And yet, the United States has done literally nothing about this. We must start now to apply science in developing synthetic liquid energy sources, and hopefully not ones that compete with resources used to grow our food supply. And then down here in red, which is kind of hard to read, we must create sustainable energy sources not dependent on fossil fuels and that do not pollute our land, our air, or deplete other resources. And I don't know when that's all going to happen. This shows Greenland, and the bottom line is that in 2002, the Greenland ice cap had melted back considerably from where it had been in, oh, I can't read that now. 1992. It's nice being in the audience. So now I'm really going to switch a lot, talking about how advances in science are made and what they do. So this is James Dewar, who's one of my favorite people because as a low temperature physicist, I use James Dewar's flask, the Dewar flask for holding my liquid nitrogen and my liquid helium. But Dewar, by the way, was Scottish. That's not terribly relevant until we get to the next slide. So these are the years that he lived. But Dewar was in a competition with this man here, Heikki Camerlionis, who was a Dutchman. And these two, I dare say, were vying for whoever could do make devices that would be most useful. And I suppose that it really, the person that won that game was Camerlionis. What he did, though, well, I have to go back. Okay, so what Dewar was doing was actually systematically measuring the temperature at which various atmospheric gases liquefied and where the liquids solidified. So he was doing this for virtually everything. And so Camerlionis decided he would try to do something similar, but in fact, Dewar had actually done most of the interesting gases. One that he hadn't touched was helium, which is one of my favorite substances, helium gas. So he then tried to, so he did exactly what Dewar had done. He liquefied the helium. I think we all know that helium is a liquid at atmospheric pressure at 4.2 Kelvin. But then he tried to solidify helium under its own vapor pressure. And he worked on that for a long time. The trouble is that helium actually does not solidify under its own vapor pressure at any temperature. Even I've cooled helium down to 1/10,000th of a degree above absolute zero, and it stays very happily in a liquid state. I will confess that I was actually cooling helium-3 and not helium-4, but the same thing would have been true for helium-3. So Camerlionis decided he needed to do something different, and so people are debating what would happen to the electrical conductivity of a very pure metal if you cooled it all the way to absolute zero. One school of thought was that at some temperature, in fact, the electrical conductivity would cease. And so Camerlionis got a very pure sample of mercury, which is a metal, it's a liquid actually at room temperature, but it is a metal that's very easy to purify. So he had very pure mercury, and he instructed his associate Gilles Holst to measure its electrical resistance as a function of temperature. So this is the resistance 0. This is 0.0005 ohms. This is 1,000th of an ohm. Anyway, these are very small resistances. So the resistance is in fact dropping as he's cooling it down. This is 4 Kelvin. This is 4.5 Kelvin. And then all of a sudden, there was a precipitous drop of the electrical resistance to a value which was, as best they could tell, less than 10 to the minus 5 ohms. This was, of course, the first observation of superconductivity, something that has been studied, I dare say, ever since that time. So it was kind of exciting. This is not something that they expected to see, but in fact, this opened up a new world for low temperature physicists such as myself. But now I'm going back a bit in time. So I now want to talk about more broadly about a lot of advances and what they've done for mankind, other than kind of making money for some people. So this is paleontology, and of course, this looks like a Tyrannosaurus Rex. I'm not sure that's what people are nodding their heads. Either they're getting, I have put some of you to sleep, or you're agreeing with me. I can't tell which one that is. But anyway, so I mean, this is really kind of, because it's important because this is where we came from. I mean, we didn't come from. I don't think I'm faintly related to this animal here, but in fact, you can see through studying the fossil remains of animals, the evolution of the species and the growth of different species. So, life on Earth and our place in the cosmos. The study of fossil remains of animals and plants that lived millions of years ago provides us with an understanding of the history of life on our planet. This is a story which helps us to better understand the origins and evolution of life on Earth, and it also helps us to appreciate the complex processes that produce the human race. At least for some of us, we may think that's the case. The evidence suggests that this planet is some 4.5 billion years old, and that our universe is some 14 billion years old. Our sun is one of perhaps 100 billion stars in our galaxy, and with the Hubble Space Telescope, we can estimate that there are approximately 100 billion galaxies presently observable from Earth. So we are certainly not alone. It's unlikely that we're alone. So these studies do not enable us to create new technologies to improve our lives, but they do help to improve our intellectual well-being, and the technologies developed to make these studies can and do find other uses, some of which do benefit mankind. So now we're going on. This is Charles Darwin. Now I dare say, I've got to brag a little bit here. I will be going to the Galapagos Islands in another month. Really exciting thing to do. Anyway, of course, Charles Darwin is the person that did visit the Galapagos Islands. And by looking at the different species of animals on these isolated islands, he in fact developed his theory of natural selection and published his book on Origin of the Species. And this really was a phenomenal, I would say, giant leap for mankind in our understanding of the evolution of animals on Earth. Well, this is James Clerk Maxwell. I think everyone that's taken a course in electricity and magnetism appreciates the fact that Maxwell, while looking at the equations that describe electric and magnetic fields, recognized that there was one term missing. And when he put in that last term, he realized, in fact, that electromagnetic waves should propagate. And so electromagnetic waves include radio waves, microwaves, light, X-rays, and gamma rays. Really quite remarkable what one tiny term that I'm sure lots and lots of high school or even college students probably left out at one time or another. So this now is Alexander Fleming, and who was the person that he got the Nobel Prize for penicillin, and of course this was just the start of a rash of wonder drugs that really saved a lot of people's lives. So, but if you look at the bottom here, healthcare in the United States costs $2.4 trillion. That was in 2007. So you get what you pay for, or you pay for what you get, I suppose, in some sense. So this is kind of an interesting story, and it's kind of a sad one. This is the DNA double helix. And the Nobel Prize for discovering the double helix went to James Watson, Francis Crick, and Maurice Wilkins in 1962. But really, there's someone else that deserves to have that prize or share that prize, and that's this person here, Rosalind Franklin. I don't know how many people here know the story about Rosalind Franklin, but in fact, Wilkins actually got one of her X-ray crystallography pictures and ported it to that other group of people that were working on this. So ultimately, well, what happened, unfortunately, was that Rosalind Franklin died. So that's probably the main reason why she didn't get the Nobel Prize. But there is I don't know if it's available now. There was a play called Photograph 51. I don't know how many people have seen that play. Oh, it was a spectacular play. Oh, you did? Okay. It was amazing. Unfortunately, she died, but I think she really deserved to share the prize. There is a problem with Nobel Prizes. You cannot give the Nobel Prize to more than 3 people. And so that's why this sort of things happen. So, okay, well, now we're getting into my realm. I use nuclear magnetic resonance for a lot of my research. So, but it's hard to explain what nuclear magnetic resonance is to a lay audience. I don't know how lay you guys are. But you can imagine that the nucleus of an atom is like a spinning top. However, it has a nuclear, because it has charge, as it spins, it creates a magnetic field. And that magnetic field, well, I have it here. Just as the gyroscope precesses about the Earth's gravitational field, when the axis of rotation is tipped away from the direction of the gravitational field, now we have a magnetic field B, and we're tipping the spin away from that. The nuclear spin precesses in a magnetic field when the direction of its spin is tipped away from the direction of the magnetic field. The nuclear spin carries a magnetic dipole moment. As this moment precesses, it generates an oscillating voltage, which can be sensed in a pickup coil. The strength of this voltage depends upon the number of spins precessing, and the frequency of this oscillating voltage is the same as the frequency of the precession of the spin itself. So this really explains how NMR works, and I dare say I started doing NMR, I think, when I was an undergraduate at Caltech. But now, in fact, first I should give credit where credit's due. NMR was invented by these two people, Felix Bloch at Stanford University. I should say Felix Bloch at Stanford University and Purcell at Harvard. Actually, I didn't know Felix Bloch. He died before I became a professor at Stanford. But Ed Purcell is one of the kindest, gentlest, brightest people I've ever met in my life. I think he's dead too, I'm sure. But he was a really, if I had hero figures in my life as a scientist, Ed Purcell was one of them for sure. So this shows the evolution of nuclear magnetic resonance. I showed you its inception. I was actually interested, I was looking at a mixture of liquid and solid helium-3 under pressure, about 34 bars of pressure. So you had some liquids and some solid helium-3, and I wanted to separate out the NMR signal that came from the liquid helium-3 from the solid helium-3. I did that by applying a magnetic field that was larger at the bottom than it was at the top. And so then if I applied a single frequency to this NMR coil, I would generate a resonant layer. And if I swept that frequency upward, that resonant layer would move downward where the magnetic field was largest. So this, in fact, was an early form of MRI. And in fact, I actually sent a preprint of my paper describing how I did that to the people, mainly Paul Lauderbur and Peter Mansfield used a much more sophisticated form of MRI to image. This is a very healthy human knee. Now, this knee is titanium, and this one is not very healthy. Okay, but in fact, you can do actually a much better job at seeing some of the details inside the human body using MRI. And in fact, it doesn't involve any ionizing radiation. It's really a very benign thing. So for, basically, Laureate and Mansfield shared the Nobel Prize. But it's interesting, if you look all over, for all of the Nobel Prizes that were given for advances in nuclear magnetic resonance, there are 4. It's a really remarkable technology. And this is the last. This one hasn't won a Nobel Prize, but I think it should. This is called functional MRI, magnetic resonance imaging. And what happens is Seiji Ogawa and David Tank created pulse sequences which allowed them to see those places in the brain that were processing information. So you can't tell what the patient is thinking, but you can see where, in fact, his brain is actually functioning. It's absolutely amazing technology. Okay, so we're off of NMR. Some people are saying, thank God he's done it. It's terrible when people are talking about something that they love deeply. The rest of you can't resonate with that, I understand. So we're going on. We're going. I know deep down in your heart you would love to have known more about NMR. And if you come to one of my lectures, I'll tell you. Anyway. So this is kind of, we're really going back in time now, I suppose. This is Carl Jansky, who is working for AT&T Bell Laboratories. I worked for AT&T Bell Laboratories myself for many years, 20-some years. And so AT&T saw some extra noise that they didn't understand, and they asked Carl Jansky to kind of find out where that noise was coming from. So he created a very strange looking radio antenna, but what he basically found was that the noise was coming from up there. Okay, it was coming from outside our atmosphere. And so this was really the start of something big. So in 1978, Arnold Penzias and Robert Wilson, who had done a lot of work studying this, actually shared the Nobel Prize. But it's kind of interesting. This is the device that Penzias and Wilson used. Now, it was basically a horn antenna that AT&T had used to basically look at the feasibility of using satellites to basically do telephony. That is to say, you could beam a signal up to a satellite and then beam it down to a base station somewhere else. And so this is the device that did that. And when AT&T was done doing their tests on this, they gave this piece of equipment to Arnold Penzias and Penzias and Wilson. And so they then wanted to look at radio signals coming from extraterrestrial sources. Really, the reason this is a horn antenna, which means it's very you can point it in a specific direction. But inside this shed was in fact the greatest technology of its day. And it's Charlie Towns. This is basically ammonia maser 2. This is the second ammonia maser that Charles Towns made. And in fact, this was, of course, a prototype for lots of other things. Ultimately, Nicholas Bloombergen at that other university of the East Coast, people at Stanford have trouble pronouncing Harvard. So,
Charles Towns in there?
that's Charlie. This is Jim Gordon, who I think was working with Charlie at that time. Anyway, so this was, in fact, the start of something very big. I mean, this thing, huge thing, was actually not the technology that ultimately was useful, but in fact the fact that this work led people on to do other things. Well, I guess I missed that one. So we're going on though, looking at other things. AT&T had been using, what were they using before transistors? Tubes, electron tubes. And they produce a lot of heat, and they're not small. And so the AT&T went to John Bardeen and asked Bardeen if maybe he could put together a group. They were all at Bell Laboratories. Invent some solid state device which would basically allow us to not have to use electron tubes. And so Bardeen, Bratton, and Shockley invented the transistor, and I dare say that is not the technology that we use in our radios and television sets today. Oh, so here's I think this is iPhone 3. I've got iPhone 5. Most of you probably do, and you can compare this with this. How many people here? I want you to be honest. Raise your hands if you ever used a dial phone. That's impressive.
How many people have not?
Okay, how many people have not used a dial phone? They're all young. They're all young, as you can imagine. Okay, so this is actually the computer. This is exactly the computer that I'm using right now. Okay, so I'm changing gears quite a bit and really talking about the progress of technologies. And of course, NASA sent 2 robots to Mars. And I think no one expected those robots to last the first winter, but in fact, I think their third year. I mean, it's amazing what a technology. And the idea that we control something that's on the surface of Mars, it brings goosebumps to the back of my neck every time I think about it. So really quite a remarkable technology. So this is the Hubble Space Telescope, which really allowed us to look at astrophysical objects further away than we've ever been able to see before. This isn't one of those things, but I just went to get something that looked interesting. This is a spiral galaxy. So I have to say that NASA's done some wonderful things, but I'm afraid that the space shuttle wasn't one of them. I was actually on the board that investigated the Columbia shuttle accident, and that was an accident that never should have happened. It was a terrible, terrible mistake, and there's no reason why all of the people on board should have perished. This wasn't the first accident. This was the second accident. So you might say, well, they surely learned after their first accident. That was where they had hot gases leaking through these rubber O-ring seals. But anyway, so I was on the board that investigated the Columbia accident. I remember exactly what happened when I came home and told my wife that they'd asked me to be on the board to investigate the Columbia shuttle accident. I was also chairman of the physics department at Stanford University, and my wife said, "Don't you do that, don't you do that." That was the most fascinating thing I've ever done in my life. It was very sad, but it was fascinating. Okay, so here we're back to Penzias and Wilson again, but now in fact we look at the final, basically this is their view of the cosmos. And you see these fluctuations in the temperature of the radiation that's coming from various parts of the sky. The average temperature is 2.725 Kelvin. But in fact, what we understand now is that the fluctuations in the temperature were due to fluctuations in the density of the early universe at the point where basically matter and energy separated. And so you basically have some of this is hotter than other places. I think I'm getting, okay, so we're almost done. So this is, of course, how many people recognize where this is? This is Red Square, okay, looking down. So this is a typical satellite, and during a period of time where we wanted to know what the Russians were doing, the Russians wanted to know what we were doing, I suppose that these downward-looking satellites actually were important for peace. They really were. But now, in fact, I can go to, this is Red Square, St. Basil's Cathedral in the background. A little bit of snow didn't hurt. And so I'm mainly a very avid amateur photographer, but I love going around the world and getting these pictures. So this is, in fact, you don't have to look down anymore. You can actually go to Red Square. You can see all of these things. You don't have to worry about being thrown into the clinker. This is right inside the Kremlin itself. This is an old canon. It has nothing to do. But the idea that I, as an American citizen, could be inside the Kremlin was just absolutely amazing thing for me. Okay, so we're almost done here. This is December 11th, 2001. That was the, does anyone know what happened on that date, 100 years earlier? That was the first Nobel Prize was given out at that time. And so this is, so I was there, they had all of the Nobel laureates came back, which is a lot. And so they didn't, this is a banquet table. I think it's sat something like, I don't know, over 100 people. Thank God I wasn't there. They didn't have enough room, so I was out, in one of the large areas. But the trouble with, if you guys ever have the opportunity, keep in mind that if you're one of these banquet tables, you can only talk to the person on your left and your right. You can't talk to anyone else during the entire, so make sure that person is really a really interesting person. Anyway, so this is kind of fun. All right, so I should say this is my wife. This is Harold Kroto, who also had a Nobel Prize, and this is Lady Kroto. But does anyone know who this guy is?
That's you.
No. Count Sawala. That means I laugh myself to death. No, this is, so this is Fred Sanger, who won 2 Nobel Prizes for protein and for DNA sequencing. And you didn't even know who it was. Shame. So there are a handful of people that have won 2 Nobel Prizes, but it's a very, very small group. Okay, so now I really completely collapse. I'm one of the things I love is, as a Nobel laureate, you get to go all over the world, and I always bring very expensive cameras with me. So this is a picture of Hong Kong Harbor at night from Victoria's Peak. And it's kind of interesting because I took this picture, and then almost a year later, I went back up there and took the daytime picture of it, and it was kind of fun. Anyway, so this is okay. So this is Hong Kong. This is Iguazu. This is at basically the border between Paraguay and Brazil. This is actually only a small piece of the Iguazu Falls, which is a really incredible thing. I had gone to there was in Paraguay there was a fine arts school, and they wanted to give a talk there, and so I quickly looked in I Googled and found the really interesting stuff that was within 5 hours drive. And so I said, okay, if you take me to Iguazu Falls, I'll give you guys 2 lectures. I was being generous. Anyway, so this is, of course, we don't have to go very far to see the Big Sur coastline here, but it's one of the more spectacular of the sites. This is Dunhuang in western China. This is a very complicated story. I was giving a talk in Beijing. There was a delay, and I said, well, what can we do about that? And I said, well, okay, we'll just fly you to Dunhuang. And so that they knew what I liked. Okay. So anyway, that's kind of fun. This is a sort of a sad story. This is the Moreno Glacier in Patagonia, Argentina. And this, and of course, virtually every other glacier is in the process of melting. It's very sad. This is a so I recommend you go down there before it's all gone. Okay, and this is finally, this is kind of an interesting story. This is Mount Fitzroy, and it's named after the captain of the Beagle. I don't understand exactly how that happened, but in fact that's the case. And I think that's about the end of it. Thank you for your attention.